In this section, we discussed the concept of specific heat capacity in relation to heat and temperature change. Greater amounts of heat are needed to raise the temperature of solids or liquids to higher values. A greater amount of heat is also required to raise the temperature of a greater mass of material. Similar comments apply when the temperature is lowered, except that the heat must be removed. For limited temperature ranges, experiment shows that the heat Q is directly proportional to the change in temperature delta T and to the mass m. These two proportionalities are expressed as follows, with the help of a constant c that is referred to as the specific heat capacity of the material. The heat Q that must be supplied or removed to change the temperature of a substance of mass m by delta T degrees is Q equals mc delta T, where C is the specific heat capacity of the substance. Solving this equation for the specific heat capacity shows that the unit for specific heat capacity is joule divided by kilogram times Celsius degree. The table reveals that the value of the specific heat capacity depends on the nature of the material. Now, let's apply the equation. What is the amount of heat needed to raise the temperature of 1 kilogram of copper from 25 degrees Celsius to 26 degrees Celsius? We start with Q equals mc delta T. The change in temperature, delta T, equals 26.0 degrees Celsius minus 25.0 degrees Celsius, which equals 1.0 degrees Celsius, and we read the value of the specific heat for copper from the table to be 387 joules per kilogram times Celsius degree. Plugging in the values, we find that Q equals 1.0 kilograms times 387 joules per kilogram times Celsius degree times 1.0 Celsius degree. This is equal to 3,870 joules. The value of the specific heat capacity depends on whether the pressure or volume is held constant, while energy in the form of heat is added to or removed from a substance. The distinction between constant pressure and constant volume is usually not important for solids and liquids, but is significant for gases, for which Cp is greater than Cv, where Cp and Cv are the specific heats at constant pressure and volume, respectively. The unit of heat used most in scientific work is the joule. However, there are other common units. One is the kilocalorie, or kcal, which is the amount of heat needed to raise the temperature of 1 kilogram of water by 1 Celsius degree. A related unit is the calorie, which is the amount of heat needed to raise the temperature of 1 gram of water by 1 Celsius degree. Another common unit, often seen in the specifications of various thermal appliances such as water heaters, is the British Thermal Unit, or BTU. 1 BTU is the amount of heat needed to raise the temperature of 1 pound of water by 1 Fahrenheit degree. A useful conversion relation is that 1 kilocalorie equals 4,186 joules. This conversion has historical significance in that it expresses the mechanical equivalent of heat, marking an important advance in the field of thermodynamics. In an earlier chapter, we encountered the principle of conservation of energy, which states that energy can neither be created nor destroyed, but can only be converted from one form to another. There, we dealt with kinetic and potential energies. In this chapter, we must expand our concept of energy to include heat, which is energy that flows from a higher temperature object to a lower temperature object because of the difference in temperature. No matter what its form, whether kinetic energy, potential energy, or heat, energy can neither be created nor destroyed. This fact governs the way objects at different temperatures come to an equilibrium temperature when they are placed in contact. If there is no heat loss to the external surroundings, the amount of heat gained by the cooler objects equals the amount of heat lost by the hotter ones, a process that is consistent with the conservation of energy. Just this kind of process occurs within a thermos. A perfect thermos would prevent any heat from leaking in or out. However, energy in the form of heat can flow between materials inside the thermos to the extent that they have different temperatures, for example, between ice cubes and warm tea. The transfer of energy continues until a common temperature is reached at thermal equilibrium. The kind of heat transfer that occurs within a thermos of iced tea also occurs within a calorimeter, which is the experimental apparatus used in a technique known as calorimetry. Like a thermos, a calorimeter is essentially an insulated container, as shown here. A calorimeter cup filled with water is inserted in the insulating container. An unknown substance at a different temperature than that of the cup and water is inserted, and the temperature change of the system is measured with a thermometer. This device can be used to determine the specific heat capacity of a substance as follows. Inside a perfectly insulating container is an aluminum cup of mass MAl filled with a mass MW of water, both at the same temperature T0. An unknown material of mass Mu and initial temperature Tu greater than T0 is placed in the water. After some time, the temperature rises until equilibrium is reached at T equals Tf. What is the heat capacity of the unknown material? Since we know energy is conserved, the container doesn't allow any heat to flow in or out, the heat gained by the water and cup must be equal to the heat lost by the unknown material. We know the heat flows this way because the piece of unknown material started at a higher temperature than the cup and the water. We know, in general, that Q equals mc delta T, where C is the specific heat capacity. So we write Cm delta T for the aluminum plus Cm delta T for water equals Cm delta T of the unknown material. Solving for the heat capacity of the unknown material, we have Cu equals Cm delta T for the aluminum plus Cm delta T for the water divided by Mu delta Tu, where the change in temperature of the water and cup is T final minus T0, and the change in temperature of the unknown substance is Tu minus Tf. In summary, the heat Q that must be supplied or removed to change the temperature of a substance of mass m by delta T degrees is Q equals mc delta T, where C is the specific heat capacity of the substance. Solving this equation for the specific heat capacity shows that the unit for specific heat capacity is joule divided by kilogram times Celsius degree. Finally, conservation of energy applies to thermal energy. The technique of calorimetry applies this idea. In our example, the heat gained by the cup and water was equal to the heat lost by the unknown substance.